Welcome to this problem-solving session. Today, we'll tackle the problem distribute candies to people. In this problem, we'll explore how to distribute candies among people in a systematic way, step by step. Let's dive in and break it down together. In this problem, we have n people standing in a line, and our task is to distribute a given number of candies among them. The distribution follows a simple pattern. You start by giving 1 candy to the first person, 2 candies to the second person, and so on, incrementing the number of candies given to each subsequent person until you reach the nth person. Once you reach the end of the line, you circle back to the first person and continue the sequence with the next number. For example, if there are 4 people and 7 candies in total, the distribution would begin with the first person getting 1 candy, the second person getting 2, the third person getting 3, and the first person getting the remaining 1 candy when the sequence restarts. The goal is to return an array where each element represents the total number of candies received by each person. The output for this problem is an integer array of length n, where each element corresponds to the total candies received by that person. Let's look at an example to make this clearer. Suppose we have 7 candies and 4 people. The distribution starts with person 1 getting 1 candy, leaving 6 candies. Then, person 2 gets 2 candies, reducing the total to 4. Next, person 3 gets 3 candies, leaving only 1 candy. Finally, person 4 gets the remaining 1 candy, and all candies are distributed. The resulting distribution is 1, 2, 3, 1, which is the output array. Here's another example to solidify the concept. Imagine we have 10 candies and 3 people. The distribution begins with person 1 receiving 1 candy, reducing the total to 9. Then, person 2 gets 2 candies, leaving 7. Next, person 3 gets 3 candies, and the total reduces to 4. At this point, the sequence restarts with person 1, who now receives 4 candies, exhausting the total. The final distribution is 5, 2, 3. In this case, person 1 received candies twice, 1 in the first round and 4 in the second. Now, consider a scenario with 15 candies and 5 people. The distribution begins as usual. Person 1 gets 1 candy, leaving 14. Person 2 gets 2 candies, reducing the total to 12. Person 3 receives 3, leaving 9. Person 4 gets 4 candies, bringing the total down to 5. Finally, person 5 receives the last 5 candies, exhausting the total. The distribution here is 1, 2, 3, 4, 5. Notice that in this case, the total number of candies exactly matches the sum of the first 5 numbers, allowing for a perfect completion of one cycle. There are a few important constraints and edge cases to consider. First, the number of candies can be as large as 1 billion, while the number of people can go up to 1,000. This means the solution must handle large inputs efficiently. For edge cases, if the total number of candies is smaller than the number of people, only the first few will receive candies, while the others get none. If the total candies are exactly divisible by the number of people, the distribution will evenly complete one cycle. On the other hand, if there aren't enough candies to complete a cycle, the program must allocate the remaining candies correctly. These considerations ensure the solution works for all scenarios, from small inputs to large-scale distributions. To solve the problem of distributing candies, the brute force approach offers a straightforward and intuitive solution. The idea is to simulate the process step by step, starting with the first person and distributing candies incrementally in amounts of 1, 2, 3, and so on. This process continues in cycles, looping through all the people until we run out of candies. For implementation, we use an array of size n, initialized with zeros, to keep track of how many candies each person receives. Then, we use a loop to distribute candies incrementally, reducing the total as we go. If the remaining candies are less than the amount we need to distribute to the current person, we simply give them all the remaining candies and stop. While this method is easy to understand and implement, it has a significant drawback. Its time complexity depends on the total number of candies. For very large values, this incremental process becomes inefficient. The space complexity is relatively small, requiring only an array of size n, but overall, this approach is not suitable for scenarios with a high number of candies due to its inefficiency. An optimized approach provides a more efficient solution by taking advantage of the mathematical properties of the problem. The key insight here is that the total number of candies distributed in k rounds forms an arithmetic sequence. Using the formula for the sum of such a sequence, we can calculate the total candies distributed in k rounds as k plus 1/2. This allows us to determine how many complete rounds can be distributed before running out of candies. Once the total number of rounds is identified, we can distribute the candies for these rounds person by person, and then handle any remaining candies separately. This approach significantly reduces the number of operations because we are no longer iterating through each candy individually. The time complexity of this method depends on n, the number of people, as we only need to loop through them a few times. The space complexity remains the same as the brute force approach, requiring an array of size n. Overall, this method is much faster and better suited for cases where the number of candies is very large, as it minimizes redundant computations. After evaluating both approaches, the optimized solution stands out as the clear choice for this problem. While the brute force method is simple and easy to understand, it becomes impractical when dealing with a large number of candies due to its inefficiency. The optimized approach, on the other hand, leverages the mathematical properties of arithmetic sequences to minimize computations and achieve the same result much faster. This makes it highly scalable and well suited for constraints where the number of candies can be extremely large, such as up to 10 to the power of 9. The critical insight lies in recognizing the pattern of candy distribution as an arithmetic sequence, allowing us to skip unnecessary iterations and directly calculate the results. This balance between clarity and performance makes the optimized approach the ideal solution for this problem, ensuring both efficiency and accuracy. In this problem, we are tasked with distributing a fixed number of candies among a group of people in a cyclic order. The distribution starts with the first person receiving 1 candy, the second person receiving 2 candies, and so on, incrementing the number of candies given in each step. Once we reach the last person, we cycle back to the first person and continue the distribution until all candies are allocated. To solve this, we initialize a few variables: candies to represent the total number of candies available, n as the number of people, and an array result of size n initialized to zeros to track the candies received by each person. We also define current_candy as the amount to be distributed in the current step, starting at 1, and index to determine which person receives candies in each step. The key process here is to simulate the distribution. As long as there are candies left, we check if the current person can receive the full current_candy amount. If yes, we subtract current_candy from the total candies and update their count in the result array. If the remaining candies are fewer than current_candy, we simply give all the remaining candies to the current person and set candies to 0, as this completes the distribution. After each allocation, we increment current_candy by 1 to ensure the next person receives a higher amount of candies as required by the problem. To move to the next person, we use the formula index plus 1%n, which wraps around to the first person when we reach the last person, creating the cyclic pattern. Finally, once all candies are distributed, the result array will hold the number of candies received by each person. Some key insights include the use of cyclic traversal through modulo arithmetic to ensure the distribution wraps around correctly, the incremental increase in candies distributed, and a condition to handle edge cases where there aren't enough candies for the current allocation. Together, these steps ensure a proper simulation of the problem's requirements. The implementation uses a simple array and a few variables, making it efficient in terms of space. The result array of size n allows constant time updates for each person's candy count, while variables like candies, current_candy, and index track the state of the distribution process. For the time complexity, the loop continues until all candies are distributed. Since the number of candies distributed in each step increases incrementally, the total number of iterations corresponds to the sum of the first k integers, where k represents the number of rounds. This sum grows quadratically, so the time complexity is approximately O(sqrt) candies. The space complexity is O(n), as we only maintain the result array and a few constant variables. Here's the pseudocode to summarize: initialize the result array, distribute candies in a loop by checking available candies against current_candy, increment current_candy after each step, and use modulo arithmetic to cycle through indices. When all candies are allocated, return the result array. To see this algorithm in action, let's walk through an example. Suppose we have candies equals 10 and n equals 3. Initially, the result array is 0, 0, 0, current underscore candy is 1, and index is 0. In the first round, person 0 receives 1 candy, leaving us with result equals 1, 0, 0, candies equals 9, and current underscore candy increases to 2. In the second round, person 1 receives 2 candies, updating the state to result equals 1, 2, 0, candies equals 7, and current underscore candy becomes 3. Next, person 2 receives 3 candies, resulting in result equals 1, 2, 3, candies equals 4, and current underscore candy increases to 4. Finally, person 0 receives the remaining 4 candies, giving us result equals 5, 2, 3, and ending the process as no candies are left. Edge cases include scenarios like having just one person, where all candies go to them, or having fewer candies than people, where only some receive candies. If the candies divide evenly, they are distributed exactly as required. This step-by-step process ensures a clear and correct solution to the problem. The provided solution solves the problem of distributing candies among a given number of people in a cyclic order. Here's the detailed explanation of each part of the code. 1. Initialization. The result list is initialized to a size equal to the number of people, number underscore people. Each person starts with 0 candies. This is achieved with 0 asterisk number underscore people. 2. Distribution loop. A while loop runs as long as there are candies left to distribute. The variable candies tracks the remaining candies. The variable I keeps track of the current round of distribution. 3. Candy calculation. The number of candies to give in the current round, give, is determined by the smaller of candies, remaining candies, or I+1, candies to distribute in this round. This ensures we don't give more candies than available. For update result, the calculated give value is added to the current person's total candies. The person is determined by I% number underscore people, ensuring the distribution wraps around cyclically. 5. Update candies in round. The total candies are reduced by the number just distributed, give, and I is increment to move to the next round. 6. Return result. Once all candies are distributed, candies equals 0, the result list is returned, containing the final distribution. This approach efficiently distributes the candies in k time, where k is the total number of candies, as each iteration of the loop distributes at least one candy. The use of modulo % ensures the distribution cycles through the people repeatedly without extra checks. This is the Java implementation for LeetCode problem number 1103, distribute candies to people. The logic mirrors the Python version, with adjustments for Java syntax such as type declarations and the use of Java's math.min. The method distribute candies takes the total candies in number of people, and returns an array representing how the candies are distributed. The solution iteratively distributes candies, ensuring that no more than the available candies are given in any round, and cycles through the people using modular arithmetic. This ensures correctness and simplicity in handling the distribution. In this problem, we are tasked with distributing a given number of candies to a specified number of people. The distribution is sequential, starting with the first person and continuing in a circular manner until all candies are distributed. The twist is that the number of candies given out increases with each turn, first 1 candy, then 2 candies, and so on. If there aren't enough candies left to meet the current turn's allocation, we simply give out whatever remains. The output is an array representing the number of candies each person receives. For example, with 7 candies and 4 people, we initialize an array with zeros for each person, 0, 0, 0, 0, and a variable I to track the current turn. This sets up the process for distributing the candies step by step. In the first turn, we calculate how many candies to give by taking the minimum of the remaining candies and the current turn value. Here, give equals min, 7, 1 equals 1, so we distribute 1 candy to the first person, updating result, 0 to 1. Then, we subtract this candy from the total, leaving candies equals 6, and move to the next turn by incrementing I. For the second turn, give equals min, 6, 2 equals 2, so we give 2 candies to the second person, updating result, 1 to 2 and reducing candies to 4. On the third turn, give equals min, 4, 3 equals 3, so the third person receives 3 candies, updating result 2 to 3 and leaving just 1 candy. Each turn follows this pattern of calculating the candies to give, updating the array, and reducing the remaining candies. On the fourth turn, we calculate give equals min 1 for equals 1, as only 1 candy remains. This candy is given to the fourth person, updating result 3 to 1 and depleting the total candies to 0. Since there are no candies left, the process terminates, and the final result is 1, 2, 3, 1. Now, consider a second example with 10 candies and 3 people. We initialize the result array as 0, 0, 0, and start distributing candies. The process will follow the same logic as before, increasing the amount given in each turn while ensuring we don't exceed the remaining candies. In the first turn, we calculate give equals min 10, 1 equals 1 and distribute 1 candy to the first person, updating result 0 to 1 and reducing candies to 9. On the second turn, give equals min 9, 2 equals 2, so we give 2 candies to the second person, updating result 1 to 2 and leaving 7 candies. For the third turn, give equals min 7, 3 equals 3, and the third person receives 3 candies, updating result 2 to 3. This reduces the candies to 4. As the process continues, the distribution wraps around to the first person again for the next turn. On the fourth turn, give equals min 4 equals 4, so we give all 4 remaining candies to the first person, updating result 0 to 5. With no candies left, the process terminates, and the final result is 5, 2, 3. Finally, let's examine an edge case with only 1 candy and 3 people. We initialize the result array as 0, 0, 0, and in the first turn, calculate give equals min 1, 1 equals 1. This single candy is given to the first person, updating result 0 to 1 and reducing the candies to 0. Since there are no candies left after the first turn, the process terminates, and the final result is 1, 0, 0. From these examples, we can observe that the algorithm ensures a fair and sequential distribution of candies. The modulo operation, I%number_people, guarantees the distribution wraps around circularly, and the give calculation prevents exceeding the available candies. The algorithm efficiently terminates when all candies are distributed. With a time complexity of O, k, where k is the number of candies, this approach handles even large inputs effectively. To analyze the time complexity of our solution, we need to focus on how the total number of operations grows as the input size increases. The process of distributing candies involves a loop. In each iteration, the algorithm attempts to distribute a specific number of candies, equal to the iteration index plus 1. For instance, in the first iteration, it gives 1 candy, in the second, 2 candies, and so on, or it distributes what's left if there aren't enough candies. Now, the total candies distributed after k iterations can be represented by the sum of the first k natural numbers, which is given by the formula k plus 1/2. The loop continues until this sum meets or exceeds the total number of candies available. To determine the smallest k that satisfies this condition, we can solve the inequality k plus 1/2 equals candies. Using the quadratic formula, we find that k is approximately equal to -1 plus sqrt, 1 plus 8 candies/2. This shows that the number of iterations grows roughly in proportion to the square root of the total candies, providing an initial estimate of the time complexity. Given that each iteration of the loop performs a fixed number of operations, like calculating the candies to distribute, updating the result array, and adjusting the remaining candies, the time complexity of the algorithm is determined entirely by the number of iterations. Since we've established that the number of iterations is proportional to the square root of the total candies, the overall time complexity of the solution is O, sqrt, candies. Now, for the space complexity, the algorithm only uses a single array, result, to store the candies distributed to each person. The size of this array is determined by number_people, which remains constant for a given input. Other variables, such as candies, I, and give, use constant space as well. Therefore, the space complexity of the solution is directly proportional to the size of the result array, resulting in a space complexity of O, number_people. Let's compare this optimized solution to a naive or brute force approach. A naive solution would involve iterating over the candies one by one, distributing them cyclically to each person. This means that for Candies total Candies, the algorithm would perform Candies operations, resulting in a time complexity of O Candies. In contrast, the optimized solution leverages the arithmetic series to distribute Candies in chunks, reducing the number of iterations to approximately the square root of the total Candies, which gives us O sqrt Candies. Both the naive and optimized approaches have the same space complexity, O number_people, as they both use an array to store the distribution. Additionally, the best, average, and worst case scenarios for this problem all result in the same time complexity of O sqrt Candies, since the number of iterations depends solely on the total number of Candies. The space complexity remains consistent as well, at O number_people, since it is independent of the number of Candies. To further solidify the time complexity of O sqrt Candies, we can use a mathematical proof. The loop in the algorithm executes k times, where k is the largest integer satisfying the condition that the sum of the first k natural numbers, k asterisk, k plus 1/2, is less than or equal to the total Candies. Mathematically, this means k asterisk, k plus 1/2 equals Candies, k plus 1 asterisk, k plus 2/2. Solving this inequality for k confirms that k is proportional to the square root of the total Candies, which proves the time complexity of O sqrt Candies. On the other hand, the space complexity is determined solely by the result array, which has a fixed size based on the number of people. Since this size does not change with the number of Candies, the space complexity is O number_people. These proofs validate that the algorithm is both time-efficient and space-efficient relative to the input constraints. One of the most common mistakes when solving problems like this is ignoring edge cases. For example, if the input is empty, 0, or has only one element, it might behave differently compared to general cases. This can result in runtime errors, such as division by 0 or accessing an out-of-bounds index. Another frequent issue is off-by-one errors, which happen when you mistakenly use the wrong range in loops. For instance, iterating from 0 to n1 instead of 1 to n might skip elements or lead to invalid indices, ultimately producing incorrect results. Additionally, relying on brute force solutions when more efficient options exist is a major pitfall. While brute force might work for small test cases, it often fails on larger inputs because of time limits. Lastly, misunderstanding the problem requirements can lead to invalid solutions. For example, assuming the input is always sorted or contains distinct elements when the prompt doesn't guarantee these conditions can cause your code to fail critical edge cases. Inaccurate complexity analysis is another mistake to watch out for. Overlooking the cost of nested loops or recursive calls can lead to underestimating the time complexity of your solution. This might mislead you into implementing something inefficient. Now, when it comes to interviews, there are some key insights to keep in mind. First, focus on recognizing common patterns, such as sliding windows, binary search, or dynamic programming. Identifying these patterns quickly can save you valuable time. It's also important to clarify inputs and outputs with your interviewer. Confirm constraints and edge cases. Ask whether input might include negatives, duplicates, or large data sizes. If you recognize that a brute force solution is inefficient, explain the limitations and propose optimizations. Testing your solution against edge cases, like the smallest, largest, or empty inputs, is essential. Finally, clear communication is critical. Walk your interviewer through your thought process, especially if you encounter challenges, to demonstrate your problem-solving approach. Understanding related problems can also deepen your problem-solving skills. For instance, LeetCode 1-2 sum is a classic problem that uses hash maps or two-pointer optimization. LeetCode 53 maximum subarray involves dynamic programming and Cadence algorithm, which are foundational techniques for solving array problems. LeetCode 121 best time to buy and sell stock is an excellent example of applying a greedy approach to optimize an array-based problem. Finally, LeetCode 238 product of array except self leverages prefix sums and space optimization to solve a challenging problem efficiently. By practicing problems like these, you'll start to recognize common approaches and strategies that can be adapted to new scenarios. When approaching a problem, you might start with a brute force solution. This approach is simple to implement and can help you verify correctness, but it's usually inefficient for larger inputs. The trade-off here is that while brute force has high time complexity, it's easier to write. On the other hand, optimized algorithms, such as those using divide and conquer, dynamic programming, or greedy techniques, provide better performance. However, these approaches require a deeper understanding and can be more challenging to implement. Space-time trade-offs are also worth considering. For example, using additional space, like hash maps or auxiliary arrays, might significantly reduce time complexity. The trade-off, of course, is increased space usage. The key takeaway is to focus on writing clean, modular code and testing it thoroughly. Always aim for the most efficient solution that stays within the given constraints, balancing time and space as needed. Great job! In this session, we broke down the distribute candies to people problem and explored an intuitive, brute force approach. Remember, mastering these foundational techniques is key to solving more complex problems. Thanks for watching, and keep practicing to hone your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!